So it's a pleasure for me to introduce Hans-Joachim Hein, talking about Calabi-Yau manifolds with isolated conical singularities.
Thanks. Always a pleasure to be back out here. So I'll talk about a joint paper with Sun, who you all know very well, that we put in the archive earlier this year. And the main point of the paper is that there exists Calabi-Yau manifolds with isolated conical singularities. I thought that it doesn't do anybody any good to learn about Calabi-Yau manifolds with singularities if you don't know what a smooth Calabi-Yau manifold is. So I thought I'd start by telling you about the Calabi-Yau theorem for smooth manifolds. So that's a classical story about Yau's work in the 70s. Then start looking at what happens if you have a family of smooth Calabi-Yau manifolds that degenerates require singularities. So this is where these conical singularities are going to come from ultimately. In complex dimension 2, this is completely understood. This is very classical, what happens in this case. Much less was known in higher dimensions, complex dimension 3 and up. And this is where our theorem makes a new contribution to clarify the behavior in some cases completely. So that's going to be the end of the talk. Calabi-Yau theorem is a theorem about solutions to Einstein's equations in Riemannian geometry. So I'll start with that. Start by looking at a Riemannian manifold XD that satisfies Einstein's equation. Einstein's equation says that the Ricci tensor of the Riemannian metric be equal to a constant multiple of the metric tensor. So as you probably know, the Ricci tensor is some sort of average measure of the curvature of the Riemannian manifold. It doesn't contain the complete information about the curvature, but sort of enough in some average sense. Lambda is a constant, the Einstein constant. I think the way that most people in the field think about Ricci curvature is that the metric is a tensor field. Ricci curvature is it's a curvature quantity. It's composed out of second derivatives of the metric, so some sort of second order differential operator. And in some sense, the way most people would think about it is that the Ricci curvature of a metric is like the Laplacian of a metric. So in particular, if you're setting lambda equal to 0. Looking at metrics with 0 Ricci curvature as harmonic Riemannian metrics in some sense. That's not a bad analogy at all to think about. Ricci curvature. It's some sort of natural second-order elliptic PDE that you can impose on a Riemannian metric, and in some sense it's the only one, it's the only reasonable one. So examples of solutions to Einstein equations are sort of trivial examples, trivial solutions that you have in all dimensions. And that's spaces of constant curvature. Euclidean space, hyperbolic space in dimension D, with their homogeneous metrics, homogeneous and isotropic metrics, constant curvature +1, 0, or -1. So those are trivial examples of solutions to Einstein's equations. In dimension 2 and 3 and low enough dimensions, all solutions to the equations are actually trivial. So constant curvature spaces, sphere Euclidean space, hyperbolic space for their quotients are the only solutions. The critical dimension in this problem is 4. So this in dimension 4 is where the problem really starts to get interesting, in some sense the physical dimension. So there's plenty of examples that do not have constant curvature, and there's sort of very little known by way of general theory, general systematic theory of solutions in dimension 4. So here's one major open problem, or largely open problem about Einstein manifolds. For me, the rest of this talk, lambda is always going to be 0, so I'm looking at metrics with 0 Ricci curvature. It's called Ricci-flat. And the major problem is to find examples of solutions to this equation, find closed Riemannian manifolds XD. That are Ricci-flat, 0 Ricci curvature. But that are not already flat, that are not already, Euclidean space or a quotient of Euclidean space. So if you want, harmonic function that's not already linear, it's not trivial in this sense. For example, I could impose the condition that the fundamental group of the manifold be trivial, and that automatically rules out the possibility that it's a quotient of Euclidean space by some discrete group. And it turns out that this is still widely open, and almost the only known satisfactory answer to this problem in any generality is provided by the Calabi-Yau theorem. Maybe before I state the Calabi-Yau theorem, I should say one more thing. Usually, if you want to solve some kind of PDE, some kind of geometric PDE, and get interesting examples of solutions, what you can do is impose symmetries, make a symmetry reduction. For example, homogeneity 1 symmetry is going to reduce your PDE to an ODE, and then maybe you can work out explicit examples that way. And you get non-compact manifolds in this way, but that's been sort of a fundamental problem for a long time. It's known that a closed manifold without boundary, compact without boundary, which is Ricci-flat, does not have any non-trivial killing fields, any non-trivial symmetries. So in a closed manifold, you can never get any non-trivial examples by some sort of symmetry reduction. That's sort of the main obstruction to progress on this problem at some level. And the Calabi-Yau theorem overcame this problem in the Kahler setting. It's a very ingenious way. So I'm going to try to explain this. So from now on, we're going to be looking at Kahler manifolds. So we're going to be assuming that X is actually a complex manifold. So the real dimension D is equal to 2n, and is the complex dimension. And I'm going to assume that the Riemannian metric that I'm looking at is a Kahler metric. So what does that mean? You have a complex manifold. This means you have local holomorphic coordinates. Not just T infinity differential, but holomorphic coordinates. Let's say Z1 through Zn. And then G being a Kahler metric means that locally it's possible to write the metric tensor in terms of the Hessian of a function. It's sort of a mixed Hessian with respect to holomorphic and anti-holomorphic coordinates. So locally I'm able to write the metric tensor as partial squared phi. Phi is some smooth real function. Potential. It's called the Kahler potential. By dzi dz bar, and this gives me the ij bar component of the metric tensor. So this is always going to be a Hermitian, a matrix-valued function with values in the Hermitian matrices, because I'm assuming that phi is real. So this defines me, a field of Hermitian matrices that I can view as a field of symmetric real matrices. And then, of course, I want to assume that this is positive definite, so that defines me a metric tensor. So this is what Kahler metrics are. And Yau's theorem tells us that within the class of Kahler metrics and complex manifolds, he's telling us exactly what the Ricci-flat ones are, and it's a very easily checkable condition. So that's the magic here. I'll just give you an example of Yau's theorem. It's going to be the main example for the rest of the talk. What's the easiest possible example of a complex manifold? It's a projective variety, hypersurface in projective space even. I'm going to say that X is the zero locus of one complex homogeneous polynomial. So X, and F. So this is all points in Cpn plus 1. So that F of Z is equal to 0. F is a generic homogeneous complex polynomial. In n plus 2 homogeneous coordinates. And if I choose F generically, then this hypersurface, this variety, is going to be a smooth complex manifold. And one part of the statement of the Calabi-Yau theorem is that it admits Ricci-flat Kahler metrics if and only if the degree of F is equal to n plus 2, is equal to the number of variables. And I can be a little bit more precise about what these metrics actually look like, at least in one special case. in complex projective space, the ambient projective space is itself a Kahler manifold that has a natural Kahler metric with a lot of symmetry that's invariant on a unitary group, is the Fubini-Studi metric. And I'm always going to be identifying Kahler metrics with the associated symplectic forms from now on. So anyway, so you have the Fubini-Studi metric, it's your canonical Kahler metric on projective space. Restricted to X, that's going to be a Kahler metric on this projective hypersurface. This is never going to be Ricci-flat, not even in the simplest examples. This is never going to be a Ricci-flat metric, so we need to correct it by some correction term that makes it Ricci-flat. And Yau's theorem says that this correction term actually exists. And the correction term takes the form of, dB bar of a scalar valued function. So there exists a smooth function C, unique up to a constant. Such that the Fubini-Studi metric corrected by del bar of this potential function is actually Ricci-flat. So let's look at some examples. The lowest possible complex dimension is n equals 1. Then we're looking at elliptic curves in the projective plane. So the elliptic curve is diffeomorphic to a torus, it's S1 cross S1 diffeomorphically. And in this case, there's nothing particularly interesting about Yau's Ricci-flat metrics, because a torus is just the quotient of the Euclidean plane, and by a holomorphic lattice of translations. So I have my flat metric on the Euclidean plane that pushes down to a flat Kahler metric on the torus. Zero curvature. And it has to be in complex dimension 1, real dimension 2. Ricci-flat is the same thing as flat. So there are only trivial solutions. Still, even in this case, the restriction of the Fubini-Studi metric is not flat. So even in this case, this correction term that you need here is actually non-trivial, and you need to solve a PDE in order to get that correction term, except that in complex dimension 1, the PDE for psi that you need to solve is actually just the Laplace equation. It's a linear PDE. And in complex dimension 2 and higher, Yau's solutions start being non-trivial, and this is exactly when the equation for psi that you need to solve becomes nonlinear elliptic PDE. So let's say n equals 2. Then X would be a particular example of a K3 surface. And in any complex dimension greater or equal than 2, just to repeat what I just said, these solutions are non-trivial. They're Ricci-flat manifolds that are not already flat, not already quotients of Euclidean space, simply because by the Lefschetz hyperplane theorem, the fundamental group is going to be trivial. it might not be immediately obvious, how useful this is, knowing that, quartic surface in CP3 admits a Ricci-flat metric. When it's, for Riemannian geometry, it's intrinsically interesting because, it's the first non-trivial solution to a really hard problem. But, the existence of these Ricci-flat metrics, especially in complex dimension 2, has applications to algebraic geometry. So, for example, for the proof of the Torelli theorem for K3 surfaces. It's one of the rare examples for a solution to a PDE at that way. Good for something. The bad thing is that we don't know very much about what these solutions actually look like. So they're given by an abstract existence theorem for a PDE. And looking at degenerations of Calabi-Yau manifolds helps us to get a better handle in some sense of what these solutions might look like concretely. What do I mean by degeneration? I'll just restrict to one particular example. So I'm going to say that my polynomial f of degree n plus 2 is now going to vary in a one-parameter family, in a holomorphic one-parameter family. So I'm going to say that f sub t is a holomorphic one-parameter family of polynomials. So t is in the unit disk, holomorphic parameter in the unit disk. X of t is x of f of t, the corresponding projective hypersurfaces. And I want to assume that the generic one is smooth, and the special one, when t is equal to 0, has some singularities. So that's my assumption. And the question is, what happens to Yau's Ricci-flat metrics on these smooth manifolds as t approaches 0? The big part of the rest of my talk is going to be to try and convince you that this is actually an interesting question because it has interesting answers. Just as a general principle, if you have a smooth structure and you let it degenerate, then the degenerate limit might be easier to understand than the smooth thing that's approximating it. You might hope to get some sort of insight into the structure of the solutions to Yau's solutions to the Ricci-flat equation that way. Those are just words. I try to convince you by examples that it's actually interesting. So unfortunately, the first example I'm going to do, it's the only one I can write down explicitly, is not that interesting at all. That's not the kind of example we want. Warning, but it's the only one that's explicit enough to actually write down. So again, when n is equal to 1. Elliptic curves. What's a typical example of degeneration of an elliptic curve? This is CP2. Everyone's favorite elliptic curve is this one that has like one nodal crossing. So that's going to be x0, singular elliptic curve. With one ordinary double point, so locally near this point, it looks like the coordinate axis in C2. So local equation for the singularity would be Z1, Z2 equal to 0 in local homomorphic coordinate Z1, Z2. Or you could make a linear coordinate transformation, and that's what I'm going to do for the rest of the talk, and write it as the sum of the squares is equal to 0. So they're linearly equivalent. Well then, imagine that thing can be approximated by smooth elliptic curves. This is x of t for t different from 0. On there you have these flat metrics, or actually just topologically these are geometrically, these are flat tori. And what happens as t goes to 0? We have a flat family of flat tori that has to degenerate somehow. There's one constraint, the way I set it up, the area of the tori has to stay constant. So you have a sequence of flat tori of constant area that has to degenerate somehow. There's only way it could possibly degenerate. It stretches to infinity in one direction, and in the other direction it shrinks. So if you think of the period parallelogram, one direction goes to infinity, the other period goes to 0. So geometrically, this is pretty boring. If you take a limit, geometrically, what happens is that you just get a line. So it drops one dimension, and the limit is just a real line. So contrasting the fact that the algebraic limit, the limit of these varieties, is actually pretty non-trivial.
Where was your area hypothesis?
Because I'm assuming that the Kahler class is the class of the Fubini-Studi metric for all of these guys. It's always a Fubini-Studi metric. So x the omega t is a family of a degenerating family of flat tori. Constant area. And then you would say that the Gromov-Hausdorff limit, the metric limit, as t goes to 0, of x t omega t, is just a copy of the real line. It's a point of Gromov-Hausdorff limit because the diameter goes to infinity. This is an example of collapsing in the sense of Riemannian geometry. Somewhat from the metric point of view, the dimension drops as you pass through the limit, even though from the complex point of view, you just have a family of curves. And collapsing is bad, so we don't understand it at all well in Riemannian geometry, so that's not the kind of example we want. And it's turned out over the past, due to the work of many people over the past 10 years, that there's a natural condition you can impose on your family. It's a purely algebraic condition that a priori rules out that this kind of thing happens. So that the metrics collapse and collapse to something of lower dimension. So I'm going to explain this a little bit more later. And this is really summarizing a lot of work by many people. We can prevent collapsing by imposing a purely algebraic condition. Namely that the singular variety, the limit, has sufficiently mild singularities in a complex algebraic sense. And the right word to use is canonical singularities. So I'm not going to define what a canonical singularity is, but the obvious point here is that in complex dimension 1 for Riemann surfaces, this is the simplest singularity you could think of, pretty much, but it's not canonical. That's too bad already. But here are two examples of canonical singularities that are going to play a role later on. The quadratic singularity, so the local model of the singular point is z1 squared plus Cn plus 1 squared equal to 0. So it's a hypersurface in Cn plus 1, the simplest hypersurface singularity you could think of. Well, that's what I wrote down here, but it turns out it's not actually canonical unless you impose that n is at least 2. That's the condition that makes it canonical. And the second example would be the sum of the cubes. The sum of the cubes equal to 0. But here I would have to impose that the complex dimension be at least 3. upshot is that if I impose these conditions that the singularities of the limit variety are sufficiently mild in this sense, then it turns out that Yau's Ricci-flat metrics do not collapse. So they have a limit space, a limit metric space that still has the same real dimension d equals 2n. I'm going to try to explain this a little bit more in the first non-trivial case, which is complex dimension 2. So what happens in complex dimension 2? Surfaces. So it turns out that for singularity to be canonical is a purely algebraic definition. And it turns out as a fact in algebraic geometry that you can actually characterize two-dimensional canonical singularities extremely easily. You can say exactly what they are. Surface singularity, complex surface singularity. This is canonical. If and only if it's actually a quotient singularity. So if it's locally bi-homomorphic. To C21 gamma. For a particular kind of finite group gamma, gamma is a finite subgroup of SU2. And they're necessarily isolated, meaning that the only fixed point of the action of gamma on C2 can be the origin. Another way of phrasing is that just to say that you have a finite subgroup of SU2 that acts freely on the unit sphere in C2.
So is canonical the same in their generality as Bornstein?
Much more special. Much more special. It's basically saying that if you take a resolution of the singularity, any resolution, then the discrepancy of the resolution along any irreducible divisor of the resolution is non-negative. So, for example, crebit resolutions, of course, So why is this a good condition from the point of view of looking at these Ricci-flat metrics? Well, this is saying that if you have a variety with only canonical singularities, it's actually a complex orbifold. The worst singularities are locally isolated quotient singularities, where the thing is uniformized by a ball in C2. And from the point of view of analysis, geometric analysis, orbifolds are pretty much the same as manifolds. If I can prove Yau's theorem on smooth manifolds, probably the same proof is going to go for orbifolds, meaning that on the central fiber of the singular variety x0, Yau's theorem goes through. It turns out that that's actually the case. There are no particular difficulties, and there exists a Ricci-flat metric on the singular variety that has orbifold singularities in the metric sense. So if you look at the metric picture, then have the singular variety with some Ricci-flat Riemannian metric, Ricci-flat Kahler metric, and metrically what the thing looks like at the singularities of this variety x0 is just like a metric cone. And so it's going to be the cone over a space form. Gamma acts isometrically on the unit sphere. You model the sphere by gamma, and then you take the cone over that in the metric sense. So the metric locally looks like dr squared plus r squared times the canonical metric of constant curvature on the sphere. R is the distance to the origin. So you have this nice Ricci-flat metric on the singular variety with relatively reasonable metric singularities, and you can use that as a starting point to proving that this is actually the limit of the smooth Ricci-flat metrics on the approximating smooth manifolds. But having the singular solution on the central fiber is the starting point for proving that. So that the Gromov-Hausdorff limit as t goes to 0 of these smooth Ricci-flat manifolds is actually isometric to the completion of the smooth part of the central fiber together this orbifold singular Ricci-flat triple form. There's by now several ways of proving this, and so maybe the most intuitive way is by using a gluing theorem. You start with a singular solution to your PDE, and you glue in pieces to smooth out the singularity and prove a perturbation theorem that makes the glued thing precisely Ricci-flat. The spaces that come in here, so the pieces that you need to glue into the singularize are examples of ALE spaces. So it's complete Ricci-flat Riemannian manifolds, and sort of asymptotic to these cones at infinity. Complete non-compact. Asymptotic to C2 mod gamma at infinity. So this is the story in complex dimension 2, and what really helped us here is the statement that a canonical singularity is the same thing as a quotient singularity, and orbifolds from the analytic point of view are basically the same as manifolds. And that breaks down completely in dimension 3 and higher, and the picture becomes horribly complicated. There was relatively little known until fairly recently. Let's see what happens when the complex dimension is recently.
Is it still true away from complex codimension 3?
What's up?
If you have something with canonical singularities away from complex codimension 3, it's still finite quotient.
Yeah, that's right.
Okay.
But the quotient singularities aren't going to be isolated anymore. And for the sake of doing analysis, this is very bad. I mean, if the singular locus consisted entirely of codimension 2 quotient singularities, then you could probably do some analysis. But the bad thing is that there's sort of embedded pieces of the singular locus of even higher codimensions where the singularities are not quotient anymore. And that's the thing that completely screws up the analysis.
So you're always assuming you have just isolated singularities?
Eventually, yes, but a lot of what I'm going to state is actually true for arbitrary, So, how do I say this? So the results I'm going to state aren't nearly as nice and complete as in the two-dimensional case, but the advantage is that they're more general. They're sort of true without assuming that the singularity is isolated, for example. But they're sort of tied together. They're very general, and for that reason, they're not particularly precise. How much time do I have?
20 minutes.
Okay, great. So again, so I'm going to assume x0 has only canonical singularities. Complex dimension is at least 3. Say that. Warning. Singularities don't need to be isolated anymore. There's one more thing I can say, that if they are isolated, the way I set it up, they're never going to be quotient singularities. Because I've been assuming, taking a limit of smooth complex manifolds, and isolated quotient singularities are not holomorphically smoothable in complex dimension 3 and up. If they are, they're never of C and low gamma type. And it turns out that the singularity. Let's say we're primarily interested in isolated singularities, and then all hell breaks loose. They're definitely not going to be of orbifold type, so I can't play any orbifold tricks anymore. If there's no good notion of analysis on these spaces, no notion of preferred metrics, anything like that. So the picture is going to be a lot. I mean, there's still some picture which I'm going to try to summarize now. But it's nowhere as nice as in dimension 2, nowhere as nice and complete. And so this is due to the work of many people over the past 5 years or so, and I'm not going to write down any names, it'll just be too many. So what do we know? First of all, there still exists some sort of singular Ricci-flat metric on the singular variety, some sort of weak solution to the Ricci-flat equation that's unique if I prescribe the Kahler class of the Fubini-Studi metric.
This is like Gauge type results?
Yes, that's right. What does weak solution mean? Well, it's fairly technical to say, but basically this means that locally the Kahler form near the singularities is del del bar of a bounded function. So we know that it's possible to pick a Kahler potential that's bounded, but if we're interested in metric geometry, we care about the Kahler form itself, and that's two derivatives of the potential. if I just know that the potential is bounded, this is telling me preciously little about two derivatives of the potential. There's a fundamental obstruction here that prevents us from saying anything intelligent about the second derivatives, except that all derivatives exist if the underlying variety is actually smooth. So at the smooth point of x0, then phi is actually going to be a smooth function. There's no useful estimates whatsoever as you approach the singularities. So I just say this again. So omega 0 is smooth, is C-infinity smooth locally on the smooth locus of this variety. So on x0, the regular locus, but no useful estimates. On omega 0. In the singularities of x0.
Don't they eventually choose phi to be continuous, actually Colder continuous? Maybe a little more.
That's true actually, but still this is just pointwise information on, it's not even one full derivative of phi, let alone two. So that doesn't actually improve anything. So from the point of view of geometry, doesn't improve. What's also true is that this thing is actually the Gromov-Hausdorff limit of these smooth approximators. That's an abstract theorem that people have been able to prove. So the Gromov-Hausdorff limit as t goes to 0 of xt omega t of the smooth Ricci-flat matrix is actually isometric to completion. Of the regular locus x0 together with this weak solution. So the metric completion here. And then, so I'm going to state two deeper properties, and I'm going to attach names to them. So what's not clear a priori is that this completion is actually homeomorphic to x0 as a topological space. So you have this smooth metric on the smooth part of x0, but that could blow up in some fairly strange way as you approach the singularities of x0. So somehow it could, sprout a boundary, even though x0 has a much smaller boundary. So it's not even clear that the completion is actually topologically the same as x0, but it turns out to be true, and that's the theorem of Donaldson and Stony. And another more recent theorem of Donaldson's son of last year tells us, so you have these singularities, and you want to understand what these singularities look like from the metric point of view. What do they look like geometrically? And there's sort of an expectation in the field, so based on comparison with what we know for harmonic maps or minimal surfaces, is that the solution should be conical in a weak sense as I approach the singularities, that they should have tangent cones. That's sort of a general expectation in the field, and what Donaldson's son did is to actually justify that expectation, that these solutions have tangent cones. At each point P of the singular locus, so this completion, the singular metric space, what's a metric tangent cone? Well, you take your metric space and you blow it up. You multiply the metric by, larger and larger factors going to infinity, and you try to take a limit in the metric sense. Let's see, the limit as lambda goes to infinity of the metric space x0, omega 0. And then fixing p as a base point, it's a point of Gromov-Alpert limit. The statement is that this limit actually exists and is a metric cone.
Lambda in somewhere?
Lambda, blow up. So lambda squared. So what this is saying is that at each singular point, these metric spaces actually look conical in a weak sense. I can explain to you what a metric cone is. A metric cone C with cross-section Y. Well, the picture is this. Y is the cross-section of something compact. You have a radius function r. If I pretend that this is a smooth Riemannian manifold, then the formula for the Riemannian metric on the cone is the r squared plus r squared times some metric on y. But the tricky thing here is that y isn't necessarily a smooth manifold, so the cross-section isn't necessarily smooth. That could be singular as well. So in particular, it's not ruled out that you could start with an isolated singularity of the original variety, blow it up, pass to this tangent cone, and that the tangent cone is actually more singular than the variety you started with. That sort of as you blow up, as you pass to the limit, there's more and more degeneration. And what that means is that even though might have started off with an isolated singularity, as you blow up, this cone is going to have rays of singularities, meaning that the cross-section has singular points, and then the cone itself has singularities along every ray that passes through the singularity of y. And there are local examples for that. That this actually happens. So the singularities become strictly worse. The tangent cone is not homeomorphic, not even locally homeomorphic to the original variety. So again, even if the point at which I'm blowing up is an isolated singularity of this variety x0, if I blow up the metric past to a limit, I could end up with something that's a good deal more singular than what I started with. And this is a metric process, so it's a fairly transcendental object that I'm constructing here. Then our theorem says the following. I'm just going to paraphrase. It says that it's actually possible in some cases to say a priori what these tangent cones are. Not just that they exist abstractly, but to give an explicit formula to say exactly, what's the Riemannian metric on y. So you don't just know that the metric is sort of conical in some abstract sense. You know exactly which cone metric it's asymptotic to a priori. And not just say what they are explicitly, but as a corollary, in all of these, I mean, in our examples, the singularities are always isolated. And in those examples, we're actually able to prove that the tangent cones also only have isolated singularities. So it's really a conical singularity in the nicest sense you could imagine. It's an isolated singular point that becomes sort of asymptotic to a cone over its own cross-section in the nicest possible sense. We also have higher order asymptotics for the metric at these points. In some cases, so that requires a fair amount of explanation, and I don't think I'll have time to get through all of it. So for very, very special canonical singularities, but the important thing is that it only depends on the singularity, so it's a checkable condition. So you have a variety, so for example, a quintic threefold in CP4, if at worst, ordinary double point singularities, that would be an example. And then we know exactly what these singular metrics look like. We know exactly what the tangent cones are.
Do you know all the cases when it's possible? Or are we just
Conjecturally, yes. But this is sort of a long way. I think that's a long way off. So these are conditions. Only on the singularities. So in particular, the singularities have to be isolated. But then the conclusion of the theorem is that actually the tangent cone does have a smooth cross-section. It's actually, the tangent cone is locally homomorphic to the variety we started with. Particularly in these cases, although it's not true in general. If we have higher order asymptotics of the metric. And then I'm almost out of time, so maybe I can just give some examples of singularities. I mean, I already said it in words, some examples of singularities where the theorem actually applies. And I should stress that those are local conditions on the singularity. So theorem. It's more general than this. If all the singularities of this mod are locally isomorphic, locally biomorphic. To one of the two examples that I worked on in the beginning, so the quadratic singularity or the cubic singularity. And I can tell you what the asymptotics are. So, in case 1, omega 0 is asymptotic to IDD bar mod z to the 2 times n minus 1 over n. This model singularity in Cn plus 1, that's highly symmetric, so the orthogonal group acts on that. SON plus 1 preserves a singularity, and there is an SON plus 1 invariant model metric that you can write down. It's not the restriction of the Euclidean metric, that's not going to be Ricci-flat. The restriction of the Euclidean metric to a singularity would be this, without the n minus 1 over n. And so curiously, as the dimension goes to infinity, it gets closer and closer to the restriction of the Euclidean metric. But this is Ricci-flat. In case 2, you can prove that the model exists, but you can't write it down explicitly. So it's a solution to some transcendental problem. Back to this point that I made in the beginning, you have these compact spaces, compact Calabi-Yau manifolds, they don't have any global symmetries. This is why you can't do a symmetry reduction to make the PDE problem easier. So no global symmetries, but sort of locally asymptotically near the singularities, at the singularities of type 1 here, they actually acquire more and more symmetries, right? This is invariant under SON plus 1. So you have this non-symmetric solution to PDE, but asymptotically it limits out and approaches something that's actually invariant under some fairly big group. But of course, there's sort of asymptotic errors that are not invariant under the group. But in this example, there aren't any continuous symmetries at all, even on the local model, because there's no Lie group that preserves this cubic form. Anyway, so I'll stop here. Thanks.
Questions?
Yeah, so the link here, why, does it always turn out diffeomorphic to the thing that you would naively think of as the link?
Yeah, that's what I was saying. I mean, in the examples we are able to treat, that's part of the conclusion that the link is actually diffeomorphic to the original link of the singularity. So original singularity is isolated, tangent cone is actually homeomorphic to the original singularity. Even though in general that's definitely, there's no reason to think that that's always the case. And there's local examples that show that this is, I mean, not examples that don't extend to a compact manifold, but there's local examples where you do have this jumping, that the tangent cone has a different topology than the original space.
And these are always the Stony-Einstein manifolds?
Sure, yeah, I mean, that's what you need, right? I mean,
right.
It's Ricci-flat, it's asymptotic to a cone, so the cone itself has to be Ricci-flat, and that's saying that y has to be Sasaki-Einstein.
Other questions? Okay, thanks for you.